All right. Good evening, everyone. Welcome to the second half of today's webinar, where we're going to be diving deeper into what are smart contracts and specifically some use cases specifically built for the Nexa ecosystem. David is going to be taking us through this. He's one of the developers at Nexa and has built some real world applications. So he is the best person to take us through to understand smart contracts on a deeper level. David, thank you so much for joining us. I know it's very early in the morning for you, so thank you so much for getting up earlier and helping us spread some education on smart contracts and specifically smart contracts on Nexa.
Yeah, no problem. Thanks for having me.
So, what I'm
Um,
going to do is I'm going to stop sharing. I'm going to hand it over to you. I'm going to let you introduce yourself to, to the community and to the learners that we have on the call. And then I know that you've got a very in-depth presentation. We will get started on that. As I said to everyone, there's a lot of information to get through. So put your questions in the chat and then we'll kind of group them together and go through the questions at the end. But David, I'm going to hand it over to you.
Thanks, Danielle. Hi, everybody. I'm David. As she said, I'm a developer with Nexa. Um, been working on and off with Nexa for a few years now. Joined full time the end of last year. I work mostly on the application side. I've done a lot of smart contracting. Um, I'm going to try to not get too in depth for those of you who are brand new to smart contracts, maybe not quite as technically inclined. I don't want to bore you with all of the details, but I'm going to give you enough background on related technology that's essential for understanding how contracts work. Let me go ahead and try to share my screen here. All right, so after that little hiccup, here we go. I'm going to talk to you about smart contracts on Nexa. You're probably wondering, some of you, what is Nexa? And so Nexa is a fair launch layer one blockchain. Um, we use a UTXO proof of work model. We are not just another token on a chain. Um, So we use the UTXO and the proof of work model similar to Bitcoin. We are not proof of stake or account based like an Ethereum style blockchain. We have a native token called Nexa. Our denominations are in Satoshis. That's 100 Satoshis is equal to one Nexa. We also include group tokens. Native issuance for those group tokens and NFTs is built right into the protocol. So that includes both fungible and NFTs. Some things which sets Nexa apart from a lot of other coins out here is our very high transaction throughput. We're designed for fast transactions. Network has been load tested at over 60,000 transactions per second to date, and we have very low transaction fees, a tiny fraction of a cent basically per transaction. Um, we've also implemented script-based smart contracts with introspection capabilities. That is a key piece of technology missing from Bitcoin currently. Um, our brief history is basically that this all started from Bitcoin. And then the network hard forked into Bitcoin Cash, and the code base of Bitcoin Cash was then forked. We significantly enhanced it, and that is what ultimately led to Nexa. So now I'm going to run you through a few foundational concepts that are essential to better understanding exactly how a smart contract works on Nexa. Um, So first off, the concept of a UTXO. UTXO is a coin. It has an amount and a locking script, also known as a constraint script. Um, in order to spend that coin or spend that UTXO, you provide a satisfier script. That makes the combined script evaluate to true. So here you can see we have a locked transaction output that is representative of UTXO1. For the purpose of this example, the amount is 20. A satisfier script is applied to that UTXO, and that creates the input to a new transaction, also with amount 20. Once spent, a UTXO is consumed and new UTXOs are created. So that UTXO with amount 20 that was input to the second transaction, in this example, splits into two outputs. Say one of those outputs goes back to me, one of them is sent to somebody else. They're both of amount 10, and that original locked UTXO1 has been destroyed. Two brand new UTXOs of amount 10 have been created by that transaction. So the real world analogy here is if you want to think of, you know, what is a UTXO in real world terms? Imagine you hand a $20 bill to a merchant, and that $20 bill is permanently destroyed as soon as you hand it over. Uh, Imagine that two new $10 bills are printed kind of out of thin air, and the merchant would keep one of those $10 bills. You would receive a new one as change. That is kind of the real world concept of a UTXO. And it is important to note that on Nexa, there is no real difference between sending coins and executing a smart contract. They're both the same thing, in essence. You're just proving that you have the right to spend a UTXO by satisfying the constraint or locking script. And essentially, that's just uh, a locking script that is slightly more complex for a smart contract versus a regular transaction. Um, you basically, are providing a valid signature for the owner's public key when it's a regular transaction. When it's a contract, you have a more complex constraint. You are maybe providing an Oracle signature, proving that a price condition was met. Maybe if maybe if there's constraints on where those outputs go, you're making sure the correct person is being paid. Essentially, whatever conditions the contract was created to enforce is enforced by that script. Once those conditions are met, that coin is able to be spent. But contracts are not a separate system applied on top of the blockchain. They're just a natural extension of the same exact spending mechanisms that almost every transaction uses on the Nexa blockchain. So now we're going to go through stack-based script evaluation. This is another essential component of understanding the workings of smart contracts. I will try to keep it high level. Um, So scripts in Nexa execute on a stack machine, very similar to Bitcoin again, Bitcoin Cash. Um, so you push data onto a stack, you execute some operations. With Nexa, there are really no official loops implemented. So this means that there's a bounded execution window. Scripts always have a termination point. There's a finite amount of instructions. Um, So what you're seeing here is on the left, you have a satisfier script and a locking script. This gray box in the middle, we're going to imagine that as a stack. So what you would do is you would first run the satisfier script. It would push that data onto the stack. You can see 4 is being pushed, next 3 is being pushed. Those are the conditions that and again, this is a very simplified script, but this script is proving that you have met some sort of conditions to spend. In a real transaction, you would be signing the transaction, the signature would be checked. This is just a toy example. Um, so next, the constraint or locking script runs and it validates the conditions. The first opcode in that script is add. So that would be pushed to the stack. Now there's a 3 and a 4. You're adding those together. You get 7. Now you push the constraint scripts 7 onto the stack. And lastly, you would push op equal onto the stack. That op equal is going to take those two items, compare them for equality. They all three disappear. The stack is now clean. And that is the condition for a valid spend. If the stack ends clean, the transaction went through. So all transactions are fully validated via network-wide consensus, meaning every single node running our script machine will agree that a script either executes or does not. Um, Now we're going to go on to the concept of opcodes. This is another concept that is very important for understanding um, how Nexa smart contracts work. So first off, most importantly, op parse. This is an opcode that uh, Bitcoin and Bitcoin Cash never got around to implementing. This is essentially the most important opcode for making smart contracts work on Nexa. OpParse essentially knows where each piece of data is inside of the hex transaction. It operates like a template and it accesses the data contained within individual fields. Some of that is hashed together, some of it is unhashed information, but it allows you to look at the transaction structure, the inputs to the transactions, the outputs to the transactions, destination addresses, so which wallets are being paid. This allows you to inspect the entire transaction structure. We also have op verify, which is just asserting a condition is true. If it's not true, the script will fail. Um, Check lock time verify is just for uh, transactions or contracts that want to enforce time-based conditions. Um, we have check sig verify, check data sig verify. Those are the signature verifications, making sure that a valid Schnorr signature was applied um, with reference to a specific public key. And then we have a bunch of other standard arithmetic comparison opcodes like add, subtract, divide, greater than, less than, etc. Um, One other concept that I want to introduce everybody to is the concept of decentralized oracles. Um, Oracles come into play in the contracts that I will show you an example of later on. We have some applications or proofs of concept on Nexa that include peer-to-peer betting and predictions. Those all hinge on what are called decentralized oracles to sign the outcome. Essentially, an oracle is a trusted provider that just signs statements about any real world event. And an oracle could be hosted online and created to sign any piece of data imaginable. On Nexa, we have a couple of oracles that we use. One of them, for instance, signs data on the prices of Nexa at given timestamps. Hourly average, daily averages. We also have another oracle that signs the scores and outcomes of sporting events. Um, so essentially, a contract would take the signature of the oracle, compare it to a well-known public key of that oracle, and just verify is the spending proof coming to this contract signed by the correct oracle. And that public key would be hard coded into a contract at compile time. We'll get into that a little bit more later. But essentially, the decentralized Oracle does not know or care about any of the contracts. It doesn't know the participants. It doesn't know who bet on what side. Um, if it is a bet contract that's being settled by your Oracle, the only thing the Oracle knows about is the score or the outcome of the event. So it simply publishes signed facts. We do have a price Oracle on Nexa where if you check in the PDF of this presentation, you can go on and take a look. We have a number of pieces of data that are signed by our Oracle here on wallywallet.org. I have gone ahead and created a slide for you, which shows if you were to click on that Oracle link, you would get a piece of information back that looks something like this. This is for an hourly average. It tells you the type. It could be a daily average, an hourly average. It also comes with a message that contains some hex data and a hex Schnorr signature. Um, the data that's being committed to in this signature is essentially these three fields down bottom. There's a timestamp, a price, and a ticker symbol of USDT and Nexa. So the information in the epoch seconds, price, and pair price unit fields is the data that's being signed. Um, you get that signature back. If it checks out, you parse out all of the data from a well-known structure, a certain number of bytes in each field, and you will get this same data back out of that out of the hex, and the signature will check out. So next we have a comparison about the difference between smart contracts on Nexa versus smart contracts on Ethereum, which is probably, for those of you who have exposure to working with smart contracts, you're probably familiar with the EVM style contracts. Um, Nexas are quite a bit different. So we have, again, the UTXO based model on our blockchain, and that extends into our contract scripts. Whereas Ethereum is an account-based model. Um, UTXO smart contracts essentially are spent one time. That contract is executed. And for the account-based ones, that contract is deployed and exists and keeps track of an internal state. So maybe multiple transactions interact over a long period of time with that smart contract. Whereas with Nexa, there is, well-known templates for contract. A specific instance of a contract can be deployed multiple times on chain, but each time it's spent from, the entire UTXO is consumed. So contracts are kind of one and done on Nexa. And if you want to reuse that contract for another transaction, you just deploy a whole new transaction with with the bytecode for that contract attached to it. We again use a stack-based script evaluation. Um, that's always evaluated anytime a UTXO is spent. Ethereum, by comparison, uses a Turing-complete virtual machine that maintains a state and storage. Um, so we are stateless, they are stateful. Um, Inputs can be validated independently on the Nexa blockchain. You can, in one single block, you could have 10 instances of the same type of contract, say the same particular type of bet that has been launched using the same contract, but for 10 different participants. All of those can be evaluated independently within the same block. For Ethereum, there is kind of sequential execution. They don't all happen at one time. There has to be an order of when transactions call a smart contract because each one of those is manipulating the state inside of the contract. Um, so we also do not have gas or any sort of fees that are contingent on the amount of execution that the script machine is performing. Whereas in Ethereum, um, everything is the more computation that is required by a contract, the higher your fees are going to be. Uh, Gas fees get to be quite a bit on Ethereum, whereas with Nexa, we have very tiny transaction fees, and the transaction fees attached to a smart contract call is again very similar to any regular transaction. You're going to pay a fraction of a penny, probably no matter how complex your smart contract is. Um, Again, we have that op parse, which lets you fully introspect and inspect the transaction structure. Whereas in Ethereum, the contracts are able to call other contracts. They can exchange state between contracts. Um, for deployment, as far as that is concerned, we essentially have a template hash that is included in the hex code that is part of the transaction. It's embedded in the UTXO at spend time, and uh, by comparison, Ethereum essentially deploys a contract that will permanently or for a long period of time live at a specific address. Um, so those are a little bit of the differences between our smart contracts and Ethereum smart contracts. Here is a mental model for how you can think of it. Essentially, Ethereum is I'm calling a function on a deployed program that changes its internal state, whereas Nexa is I'm proving that a specific transaction satisfies a specific set of conditions that were encoded and embedded into a UTXO when those coins were initially locked. So they both are fully programmable. They both enforce rules. They both rely upon cryptographic verifications. And both of them, EVM and Nexa smart contracts, are capable of third-party Oracle integration. I want to talk to you a little bit about specific attacks that exist within the Ethereum smart contracts that Nexa is able to provide a solution for because of the completely different architecture of smart contracts. So with Ethereum contracts, one of the biggest problems is and you can look back and do your own research on some of these. There was the DAO hack, Curve Finance exploit. There's been a number of issues stemming from reentrancy attacks within the Ethereum contracts. This stems from mid-contract, one contract will call, or mid-execution, one contract calls another contract, and something becomes corrupted in that contract call before it returns to the first contract. So the state is manipulated in a way that can't be resolved between the two contracts and um, essentially leaves those contracts in a broken state. Whereas Nexus scripts don't call other contracts. Again, there might be reference to one embedded in a UTXO, but a single UTXO spend or a single transaction consumes that contract UTXO, um, and then it doesn't exist anymore. So to put it simply, our contracts validate transaction structure and provable conditions. There is no reentrant path to exploit. Um, Another related attack on Ethereum contracts, or less of an attack, more of just bugs, is the state mutation bug. So Ethereum contracts are constantly modifying a persistent storage. They're updating balances, mappings, flags in the code, and bugs in any of those state transitions between contracts can leave contracts in a broken state permanently. If that contract can no longer execute correctly, all of the funds locked within it are stuck, many times unrecoverable. This is not as uncommon as you would think in EVM contracts. Uh, Again, Nexa's contracts are completely stateless. The UTXO either exists or it's been spent, so there's no mutable state to corrupt. We also talked about the bounded execution and the no gas fees. Within Ethereum, there's actually some gas-based attacks that exist. One of them is called gas griefing. There is also kind of a complex estimation that you have to do when interacting with a smart contract on EVM. You have to estimate how much gas it's going to take to perform that contract call, and you have to ensure that you have uh, enough coins attached to that transaction for whatever the transaction is that you're performing, as well as for all of the gas fees. If you miscalculate that and you are trying to spend a very exact amount and you don't want to send too much, you can end up in a situation where you call a contract, it eats up most of the gas money that you sent it, and it doesn't have enough money to continue executing and finishing with your transaction. So you end up with an out of gas revert, is what it's called. So that contract call, that transaction is canceled. You didn't have enough funds to pay for the execution of that contract. Um, that doesn't exist on Nexa. It's a straight up, very small transaction fee, and there's no guessing about it. Um, we also have what are called front-running attacks, where miners can reorder in Ethereum smart contracts. Say you have a contract that is buying and selling some sort of asset within a contract market. Um, Sometimes the market will do one thing and the prices can increase or decrease based on whether a buy happens before a sell or a sell happens before a buy. With Ethereum, miners can essentially control the order with which those contract calls happen. And so if they wanted the buy to occur before the sell contract call, they can reorder those. And maybe insert a contract call of their own before they see either a buy order or a sell order coming into that contract. So they can kind of manipulate the order with which those contracts are called and potentially profit from it. That doesn't exist with Nexa's UTXO model because again, the UTXO is spent from once and then it simply no longer exists. You can use that same contract template in a separate transaction, but that particular UTXO has already been spent. So there's no reordering. The contract call happens once on Nexa and it's consumed. Um, there's also what I mean by explicit value transfer is on Ethereum, tokens basically, token transfers happen behind a complex bunch of code in a smart contract. You don't really see the internal state changes of the code on an Ethereum contract. Whereas with Nexa, we have a very clear script. So each transaction is essentially bytecode that all translates into opcodes, those things that we talked about earlier. With an Ethereum style smart contract, it happens a lot where the code is just too complex for somebody to audit. You might have to crawl through hundreds or thousands of lines of code. If you are not a developer, you may not understand that code. Even if you are a developer, it may be too complex and may take you a long time to audit that code and understand how the value transfer is happening within that contract. With Nexa, again, once a smart contract is compiled, it all boils down to a script of opcodes. We have debugging tools like debug.nexa.org where you can cut and paste a script. You can run the debugger. It will run the whole stack through the entire script of opcodes. You can utilize many tools to ensure uh, exactly what is going on with that smart contract if that script is going to pass script machine checks. And the cool thing about our Nexa debugger is that you step through and you see at each point of the process, just like the script machine or the stack evaluation that I showed you earlier. Um, you can essentially step through it like that. You can see which values are on the stack, how the opcodes are being used. You can see the entire execution. With Ethereum smart contracts, it's just a whole lot of code to go through, and a lot of times you're taking it on faith that the developer of that contract wrote a bug-free contract and that the code will execute as intended. Um, so that is how Nexa solves a lot of the problems of EVM style contracts. Next, we're going to get into the actual smart contract part. There is a couple of things I want to explain to you so you'll understand when I show you an example of a Nexa smart contract. Um, One essential thing is that we have different types of arguments. Template arguments are essentially uh, baked into the contract bytecode at the time when it's compiled. These are values which are fixed at contract creation. These change the value of the template hash, which is essentially a unique identifier for a specific contract on Nexa. Every unique contract will have a different hash of the template. So anytime you adjust args that are template args, you are essentially changing the entire contract. It will not appear to be the same contract to users on the blockchain. It will appear as something entirely new because the contract hash changes when you change the template args. Holder args are passed in a different way that does not actually change the contract hash. So holder args are utilized. They're not done at compile time. The contract is compiled, and then holder args are attached as part of the contract script. Holder public args are also the same thing, except for instead of those contract args essentially being hashed together, they are in individual fields within the template script of the transaction. So they're easy for anybody on the blockchain to see. Essentially, holder args, think of them as being all squished together. They're hashed. It's like one giant blob of hex that represents a group of arguments, whereas holder public args are nice and neat. They are separated. They are each in a different field of the transaction hex code. Anybody on the blockchain can view these arguments, which you will see how that is useful for the contracts I'm going to walk you through. Holder args cannot be seen. Holder public args can be seen by anybody. Spender args, those are just the arguments that are passed into the contract at spend time. Those are the arguments that you must supply for the contract to evaluate a set of conditions. These could be like the Oracle signature that we were talking about earlier, a signature from another trusted party who is able to spend from that contract. Those are the types of arguments that would be passed in through spender args. Those are not at creation, only at spend time. So now let's walk through a contract in which two participants engage in a prediction on the exchange rate of the trading pair Nexa USDT at a specific future timestamp. So we're going to leave presentation mode for just a minute, and I am going to Let me get rid of these consoles. Can everybody see the screen still?
Yes. Well, I can't.
Okay.
It's quite small though. Maybe you can see
Okay.
better.
I can go ahead and blow it up. Let
Yeah, that's
me.
better. Yeah, that's better.
All right. So I know this probably looks like a lot for those of us who aren't completely technical programmers. Don't worry, I'm going to break down this contract source code for you in a very easy way. I'm just going to explain the essential parts of this contract. So I'm calling this contract a fixed time prediction. Again, this contract hinges on two participants betting on the future price of Nexa versus US dollar token. Participant A will bet that the price is going to go greater than a threshold. Participant B will choose that it is going to be less than that decided upon threshold. Up top here, we are essentially declaring a bunch of pieces of data that the contract is going to expect. These are things like timeout deadlines that would be, for an offset for an amount of time after the contract is created. How soon do you want to allow this offer to time out and get a refund? Which tickers are you dealing with? In this case, this contract is hard coded to handle Nexa versus USDT exchange rates. There is what's meant by holder A and holder B hash is essentially the hash of the wallet address that um, A or B want to be paid at. There's also a deployer args hash that would represent, say, the platform or the application who is deploying these smart contracts and maybe taking a small fee. There's a settlement time, which is a timestamp. There's the amounts that A and B are betting. And then these are the args expected at spend time, a Oracle signature, and a signed message from the Oracle. So we have a few different rules for this contract. Rule zero right here that we'll go through the script for is participant A wins. Let's call A Alice and B Bob. Alice wins with a proof. So what does this contract rule do? It checks the Oracle signature against the Oracle data that was provided. It parses out those values, getting the ticker values. It also gets the timestamp and the price from the Oracle message, and it verifies those against the hard-coded timestamp and the hard-coded target price that was passed in when this contract was created. So it just makes sure, is this target price and this timestamp what the contract was expecting? If so, then proceed. And you're verifying that in this instance, this is the rule for Alice wins. So you're checking that the Oracle signed data that states the target price or the price reach was greater than the target price. For Bob, you would verify that it's less than. And down here, this code is essentially just calculating payouts, which participants are supposed to get which amounts. In this case, you pay your fee to the platform that deployed this bet. That's your, fee for using their service. There is also a concept of a facilitator online, which is another reason why we use those holder public args that we talked about just a few minutes ago. Because those arguments are visible to anybody on the blockchain, anybody can see the arguments to a contract. They can see basically what the contract is for. They can identify it by the template hash of that contract. And our introspection opcodes here in this code that I have highlighted right here. So those are all the amounts. Right below you're basically guaranteeing that specific identities are being paid. That's what that code is doing. It's using the op parse opcode to ensure that these payments are being routed only to the correct destinations. There is one destination represents the deployer, one destination represents the winner that is implied by spending from this rule on this contract. So what is neat is we can have the concept of an on-chain facilitator. Any miner can view the arguments that are being passed into these contracts. They can see, I know this contract hash. I know this is a bet. I see from the third-party Oracle provider, maybe they write their own code to watch that Oracle service and they're running a full node, so they watch the network. They see these contract transactions going through. They know that the Oracle has a signed outcome available for that contract, and they could construct the transaction together to spend those coins on behalf of the contract participants. So the neat thing is in the Nexa ecosystem, any third party is capable of spending some of these types of contracts. The only catch is they can only spend them to the correct parties. So if I win the contract, any miner on chain could unlock the coins from the contract, but the only thing they can do with them is send to me. Their incentive for doing so is that we leave a little bit of money, off of the contract claim. We hard code these contracts to allow for a particular, usually very small fee to be taken by these on-chain facilitators. But nonetheless, it creates a new role within the ecosystem. So going further down the contract, we have a rule for B wins. It's the same thing. We're checking signatures. We are checking ticker values, timestamps. We are verifying that the price did not reach a target. We're verifying that the amounts are correct. This time we are verifying that the winner hash is actually Bob instead of Alice. And again, making sure the platform is paid, leaving some money on the table for the facilitator to claim. Our last rule is a script which is basically an exit clause from this contract. Suppose the decentralized Oracle fails to sign an outcome for a particular event. What are we going to do in that case? We're going to wait a day or 2 days, whatever the contract hard codes. It's all configurable. We are going to make sure that a particular lock time has passed. And after that time, if no Oracle proof has been supplied, then anybody can invoke this rule. It also enforces similar constraints to what we just discussed. It is going to verify the amounts and it is going to verify the payment destinations. This rule is going to ensure that Alice gets all her money back, Bob gets all his money back, and the only difference is that a small facilitation claim can be made. If Alice or Bob go offline, then cool. Any miner can claim that transaction on their behalf. The source code of the contract guarantees that though anybody can interact with that contract, there's only an Alice and Bob that can be paid. So now let's go back to my presentation, and I won't run you through all of the source code for this contract, but let me explain to you what the contract is. For sake of brevity, we have another contract which we refer to as delegation contracts. Essentially, it's a setup for that contract that we just looked at. That contract that we just looked at requires two participants at the same time to organize with each other the construction of that contract, or you interacting with a third party application who knows how to build a transaction for that type of contract. What this second contract is, the delegation, is essentially it's a one person contract. I would lock my funds into this delegation if I want to make an offer to somebody on chain, but I don't know who that person is. It's an open offer that can go to literally anybody. And the neat thing is, again, we use the concept of the holder public args, which anybody on the blockchain can view. We use op parse introspection, which again, I'm gonna keep reminding you of this. Bitcoin and Bitcoin Cash do not contain op parse. That op code does not exist for them. That's why they don't have the smart contract capabilities we have. But essentially, what you can do, I can lock my funds into a delegation contract, and it ensures that the funds can be spent only under a strict set of conditions. Anybody who is willing to construct a contract transaction of the type that we just went over, a fixed time bet contract, is what I'm delegating these funds for. We have all different types of delegation contracts, but basically what each one does is it commits to the hash of a specific contract you are willing to engage in, and it allows the funds to be spent only into that type of contract. And if it's a bet contract, the person has to meet your conditions. They have to be willing to bet the amount that you encoded into your holder public args for this contract. So if I say, I'm willing to bet on the future price of Bitcoin versus the US dollar, I want to lock this into a Nexa smart contract. I want to bet 50,000 Nexa, but I'm taking, say, an unlikely price. I want my opponent to bet 100,000 Nexa. I want them to have to wager double of what I wager. This delegation contract would ensure that the money is being spent into a contract that only cares about the price of Bitcoin versus US dollar token. It's for the same exact timestamp that I specified, and it's for the same wager amounts. So what the delegation contract is it's an on-chain offer to engage in a contract with any willing participant who is able to meet your specific terms. So that's a pretty powerful contract. Again, the source code to this contract is linked on the PDF, so if you're interested in looking through that yourself, feel free. I'm going to try to get through just the last few slides. I don't want to bore you guys for too long, but we're going to talk about the smart contract participants and ecosystem roles. So first off, we have Alice and Bob, our two participants in the prediction contracts. Those are end users making predictions on any type of, sporting events or price outcomes. We also have applications for contracts that are used in blockchain gaming, many other use cases as well. But for the sake of this example, we had Alice and Bob. We have the deployer, who is the application or the service that's being used to construct these smart contract transactions. We have the facilitator, which again, I told you about is any on-chain entity or miner who chooses to advance the state of your transaction without you having to be online. We have the third-party oracle, which is the data provider that allows you to have a proof as to whether or not you won, which unlocks your ability to spend from a contract. There's also one other role that I didn't mention that exists in certain types of bet contracts that I use. There's a super facilitator. That is a pub key that a service might hard code into a contract before compile time. And that is like one public key, one wallet, one entity that you are trusting to be able to cancel one of those delegation offers that I just talked about. So, say I make an offer open to the entire blockchain. I'm willing to engage somebody in a prediction smart contract on this event. I'm waiting for a couple hours, the odds to that event change, and I don't like that offer anymore. The only way I can get that money back is by invoking the super facilitator rule. I have guaranteed that those funds are locked, and the only way I can get a refund on that, if nobody engages me in that offer and spends the UTXO first, and I want to cancel that delegation offer, the super facilitator is the one delegated entity that would be able to spend from that cancel rule and send me my coins back. So it's another trusted third party, which some contracts utilize, some contracts do not. So what is the value that these roles and these contracts provide to the Nexa ecosystem? First off, we are it's an attempt to compete, and hopefully a bunch of users decide that they actually like the security and the safety of Nexus smart contracts more than for Ethereum smart contracts. So we're hoping to attract users from chains like Solana or Ethereum who might realize Nexus smart contracts are just as capable, and in a lot of cases, they are safer to interact with. There's also a very low barrier to interact with these contracts. Again, the super small transaction fees lend to the ability to be able to use contracts in ways that you can't on Ethereum. Try making a bet with your friend for $1 or two on the Ethereum blockchain using smart contracts. It's not going to happen. All of that money is going to be eaten up in gas fees. Nexa, anything that you bet basically that is even a cent or two would be a worthwhile bet on the Nexa platform. Our transaction fees are literally that small. And what these contracts do is the ones we ran through are simplified, just a bet between two participants. But what it shows is that there's full capability of ensuring specific parties get paid. Those specific parties get paid very specific amounts that the contracts can calculate. It allows either everybody or only very specific parties to be able to settle those contracts and spend those coins. So there's a lot of complex mechanisms within those simple contracts that shows Nexa contracts are perfectly capable to be coded for, any kind of decentralized financial applications. Also, these provide more miner revenue. The more contract transactions there are, the more ability that miners have to facilitate these transactions and earn those small bounties for advancing a contract to a settled state. And facilitators matter because this is a new way of performing a permissionless settlement. Anybody can claim on behalf of the winner. You don't have to be online when that claim is made on your behalf, but you're always guaranteed to be paid. And this creates an entire new stream of revenue beyond just block rewards and regular transaction fees for miners. So Nexa just had our first halving. Once we have future halvings, we're on the same schedule as Bitcoin. Those minor fees are going to get very small. We need to figure out a way to provide them additional revenue because miners are essentially the source of security for all blockchain networks. So current and future use of Nexus smart contracts, I'm just going to point you to a couple of applications that exist right now on our test network. These links will bring you to these services. You can check them out if you want to. You will have to download a Nexa Wally wallet in order to fully utilize these sites, but we have a battle card game. It's, essentially similar to, say, like a Magic or Pokemon. It's a battle game with NFT group tokens used instead of physical cards. So we have smart contracts which will lock a certain number of each player's cards prior to the battle. Upon winning or losing, that will determine whether you get all of your cards back or whether you forfeit one or two of those cards to the winner. So smart contracts are used for blockchain gaming. This is the prediction application where you can make predictions or peer-to-peer bets utilizing only smart contracts. The really cool part about this is normally you would interact with a sports book, you would send them your money, and you would have to trust that if you win, they're going to pay you what they're supposed to. With this, it is the service constructs a transaction that your wallet approves. As soon as your wallet approves it, all of those funds are secured within a smart contract directly on the Nexa blockchain. No third-party service is in custody of your money. You don't have to trust anyone as far as whether you're going to get that money back or not. If an Oracle proof exists stating that the team you bet on or the outcome you bet on for any given event is correct, then you have the proof to have those coins returned to you, or you can spend them. Any on-chain facilitator can do so. So those are a couple of the current use cases of Nexus smart contracts. So yes, again, we know there's so many opportunities for further implementations important to DeFi, blockchain gaming. A few ideas or contracts that we have under development would be delegation circular spends. That's one where, say, I wanted to offer a prediction of betting 1 million Nexa on to anybody on the blockchain. Somebody sees that offer and they want to accept 400,000 of that bet. They would spend 400,000 into the contract that I indicated I was interested in engaging with, and the other 600,000 would go right back into that delegation contract, ensuring that it continues to be available for any other willing participants. We can also use delegation contract, which will bind multiple parties into a contract. Instead of a two-person contract, we could have 100-person contract, 1,000-person contract. We're also going to continue to push the capabilities of op parse to be able to do more things with group tokens. We might use the group tokens for prediction markets instead of just peer-to-peer betting. You could use it for any sort of other financial applications that require, tokens that could be tradable on a market. And lastly, I will leave you with if you're interested in learning more about Nexa or smart contracts, we do have a full smart contracting library that will be coming soon for developers. Here are links to our GitLab repository. You can find all sorts of cool libraries and projects on there if you're so inclined to build anything on Nexa. Our Discord and our Telegram both have thousands of members. We do have community moderators, community managers, developers who monitor these channels every single day and interact with those in our community. So if you're interested in asking questions, join Telegram, join Discord. Somebody from our team would be glad to answer questions for you. And then here are links for nexa.org and our technical documentation, spec.nexa.org. I'll open it up to any questions and answers, and I will give this back to Danielle.
Ah, beautiful. Thank you. Definitely so much information and knowledge there. And even for me, even though like I'm not a developer and some of it was like you're speaking a whole new language, I think that it's so important for people just to understand the general kind of functionalities and some of the vulnerabilities. And one of the questions that I have, if anybody has any questions that they want to pop in the chat, go ahead and do that. I'm also mindful of time, definitely getting late over here, and then you've probably got to get on and start with your day. But you were talking about some of the potential vulnerabilities with smart contracts on the Ethereum, and I'm sure we've all heard of these different types of hacks and things that happen. And you hear of smart contract audits. to try to help prevent, whether it's bugs or whether it's, like code, backdoor code, and whatnot. So, my question is to you, with smart contract audits, do they need to particularly learn like the Nexa script language and how you guys kind of build and like all of the codes and the language of your smart contracts to be able to audit them? Like, and would that mean that particular smart contracting auditing firms would specialize in particular smart contracts? So, like, for example, smart contracts built on Ethereum and Nexa, or is it kind of universal when you're getting like anybody could audit any smart contract?
So on Nexa, again, we talked about the fact that it's a script-based language. So you wouldn't necessarily have to understand some of our programming languages in order to do an audit on a smart contract. The source code that I showed you guys was done in our Kotlin domain-specific language. Um, that is the code that I would write one of the smart contracts in. But when it gets compiled down and sent on chain, it is essentially just those opcodes. So if you understand what the opcodes do, um, or like I had mentioned, you can go to debug.nexa.org and you can cut and paste a script of opcodes into it, and you can click the play button and literally step through and see step by step exactly how that script is executing, which values are on the stack. So you can evaluate it fully with maybe a lesser amount of knowledge, I would say, than what you would have to understand. You would have to understand Solidity, programming language, in order to audit an Ethereum smart contract. So with Nexa, it makes it a little bit simpler. You don't have to learn, you don't have to know specific programming languages to audit those. You would essentially just have to learn um, to use the debugger and check if a script is going to execute or not.
Yeah, yeah, because I always hear how like important it is to, make sure that these smart contracts are audited for various reasons. So I was just wondering, in terms of like different chains, like if you're looking to build, if you want to learn how to, develop smart contracts on Nexa or on Ethereum or any other chain, then you need to learn the language, the opcodes, and whatnot to be able to kind of build out those smart contracts. So I just wasn't sure if it was the same with audits. Do you know what I mean? Like if there was kind of like certain people that would have those skills to audit a particular smart contract on a chain.
It's a much smaller audit surface than most contracts for Ethereum, and it's a little bit of a less abstract way of having to audit. It's a little bit more transparent is how I would put it. It's transparent. There's much there's much less um, content or data to have to go through and understand. And again, our entire script machine operates on a very small set of opcodes, whereas in the Solidity programming language, there are thousands of different functions that are defined within that language. So unless if you know the entire language, you or if you want to learn the entire language, then that's the only way you can really be sure of what an EVM contract is doing. There is shoot, I don't know the exact number of I don't know the exact number of opcodes that exist on Nexa right now, but it's very small. It's similar to Bitcoin with just a few added.
So does that mean, my last question to wrap it up, does that am I right in saying does that mean that the more opt codes that you have, for smart contracts, maybe the more potential for vulnerabilities?
Well, each opcode is essentially like one op could be to add two stack items together. One could be to multiply two stack items together. Another could be to take the fifth item down in the stack and swap it with the top, or to shift some of those items around. So I would say every new feature like that that's implemented is potentially like uh if it's implemented wrong, then there could be a bug in the implementation, and maybe it actually, under certain conditions, does something that is unexpected.
Yeah.
But I wouldn't really call it an attack surface, more of a bug surface. But really,
Yeah.
the benefit of adding more opcodes is that you give the script machine more functionality, and you enable things like smart contracts on Nexa, which, adding a couple of simple opcodes, Bitcoin and Bitcoin Cash could have these things, but they don't because they haven't implemented these opcodes.
Yeah, and that comes for a whole nother conversation, which comes down to like the governance and people voting in the different types of functionality within chains. But that's the questions for me. I don't see anybody putting any questions in the chat. It may be because their brain is like information overload, but I'm sure that they're excited to dive in and learn more. I have shared the links in the chat. I also shared the PDF of the slides in the chat, so if you wanted to download those, so you could have access to all of the links and everything that's in David's presentation, and for you to reach out to them on Discord. Thank you. And then if you also go to their website, I've also shared that link. It's got the link to all their socials. But David, thanks once again for getting up so early. Thank you everybody that tuned in and stayed on and learned. And just remember that this is recorded. It will be shared in the Education Hub. So please, if you know some people that will get value from this, that want to learn more about smart contracts or potentially learn how to build and do smart contracts on Nexa, go out and reach out to them. And David, once again, I don't think it will be the last time that we'll be hearing from you. I know that you guys got some more resources coming to help people that are interested in more of the developer side of things. Like I know today was not like super technical, but for non-technical people, it was probably technical enough, right? But for
Yeah.
those that want to dive deeper, I know that you guys are working on some things to try to help developers learn how to build on Nexa using like AI tools and things like that for them to stay tuned on. So thanks once again for your time.